Hello everyone, my name is Hitesh Gulcha and today I'm going to present the model architecture of DeepSeek V3. So the DeepSeek V3 is again based on the transformer architecture, um, which was the attention is all you need paper. However, there are some architectural changes. So one part is the multi-head latent attention, which replaces the multi-head attention in transformers, and the other is the DeepSeekMoE. So the feed-forward layers, some of the feed-forward layers are replaced by these mixture of experts kind of architecture, and that ensures that only a small fraction of all the model parameters are activated for each token. Both of these changes were introduced in the DeepSeek V2 paper. Although there are some changes in this paper, which is instead of having some losses for load balancing of these experts, the DeepSeek V3 they introduce an auxiliary load-free balancing strategy, and that is they have done ablation studies to say that it leads to lesser performance degradation. Again, mostly whole in whole, it's like some variation of the transformer architecture. So if you look at the transformer block, all of the language models nowadays are just decoder only models. So you would have this uh, uh, like two parts of the transformer block. Like one is the RMS norm followed by attention. Then there is a skip connection followed by RMS norm and a feed forward followed by a skip connection. So the attention part in this DeepSeek V3 paper has been replaced by the multi-head latent attention. And the key idea is to have a compressed version of the keys and values to reduce the KV cache. That's there. That kind of helps improve the memory requirements for both training and inference. And the second part, the feed forward network, it's actually the part where most of the model parameters reside. So instead of a single feed forward part, it's replaced by a mixture of experts. We'll go through in depth of this part as well. And the interesting part is just that these are sparsely activated. That is, for every token, only a fraction of all the feed forward experts are utilized, and there is some in intelligent inference mechanism by which through expert parallelism you can load each of these experts in different GPUs and nodes and have each expert only process a fraction of all the tokens. So that's what is meant by load balancing. We'll go through all of these again when we come to the DeepSeek mixture of experts. But all in all, this is the high level architecture of the DeepSeek V3 model. All right. So the first part is the multi-head latent attention. Since this was proposed in DeepSeek V2, we'll probably look at relevant sections from DeepSeek V2. So before we go to multi-head latent attention, it would be good to understand what's multi-head attention. In multi-head attention, you have different heads, and for each head, you want to find a representation of your current time step as a weighted mean of all the other time steps, like some projection of a weighted mean of all the other time steps. So basically, we use something called as the query key and value vectors. So your hidden time step is from the hidden time step, you want to calculate the query keys and values for each of the different heads. For that, you use these projection matrices, which are like DH cross D dimensional matrices. So here DH is like the dimension per head, NH is like the number of heads. So once you project it to DH cross NH, you can actually separate out the queries, keys, and values for each of the different heads. Um, and now the next task is how do you compute your output using these query keys and values. For any time step token, for any token at time step t, you find your output by taking like a weighted mean of um, all the like tokens at time steps before it, since like these are decoder only models and autoregressive, so like a causal language model, so every token can only attend two tokens on the left of it. So to get the output at token t, for the ith head, what we do is like first calculate like a soft max of the attention scores. And what are the attention scores? For this tth token, we take like a dot product of the qt with all the tokens before, with the keys of all the tokens before it. Right now the other subscript is the I, and this corresponds to the ith head. So for ith head, we take like a dot product of the tth tokens query with all the um, keys that come before it, normalize, like kind of rescale it by square root of dh, and then take like a softmax. So that gives you attention scores. The next part is to take a weighted mean of your values, weighted by these attention scores. So we are taking a summation from time step 1 to t, and then um, taking like a product of the softmax score of that attention between the tth uh, query and the jth key, and then um, multiply that with the value for that jth time step, and then basically take this summation across all the time steps from 1 to t. That gives you the output for the uh, ith head. Once you get like the output for the ith head, similarly you can compute it for all your heads, and you just concatenate, you can concatenate all of them and have like another projection to your output space to get you the output at t8 time step. So basically the output at t8 time step in multi-head attention is basically just a concatenation of your attention output from independent, like individual heads, followed by a linear transformation. And this individual output is nothing but like a weighted mean of all the values, where those weights are like the softmax of the attention scores, and these attention scores are nothing but like dot product between the queries and keys, uh, with the square root of dh in the denominator, as a scaling factor. That's like the attention in short. So the issue with the multi-head attention is that like you have a lot of the keys and the values need to be cached at the time of inference, since like once you have computed the keys and values for time, like tokens up till a particular time, to calculate the next token, you can reuse those calculations, and again for the next token after that you can reuse the calculations just up till then. So those keys and values can be reused. Hence you need to like cache 2 times nh dh times l elements for each token. So here nh is number of heads, dh is the dimension of the heads, l is the number of layers. So for each layer you need to store all the keys and values, and that makes up your KV cache, and it becomes really large bottleneck, especially when the batch size and sequence length are keep increasing. So you kind of it in a way implies like a limit on the maximum batch size and sequence length. So you want to find a way to reduce this. There are two existing other solutions called multi-query attention and group query attention. in this paper, they compared like their implementation, the multi-head latent attention, with these two existing solutions, and found that not just that it is efficient, but in terms of performance, it does perform better than both of them. So for multi-query attention, the idea is very simple. Right now, basically, we calculated like queries, keys, and values separately for each of the heads by using these projection matrices. Now, instead of having uh, like a different query, keys, and values for every head, you can have different queries for each of the heads, but the keys and the values can stay common for all the heads. So that's like the multi-query attention. And then a simpler version of that is like the group query attention, where instead of just a single shared key and value, what you have is like for groups of queries, you have like a common shared keys and value uh, vectors. So that's multi-query attention and group query attention. They proposed in this paper like the multi-head latent attention, which they show to be better than both these solutions and yet be memory efficient. All right. So now we look at the low rank key value joint compression. So the main innovation comes in like saving the KV cache is from using low rank representation for the keys and the values. So basically, first you perform like a down projection of your hidden state to something which is called the CKV. It's like the compressed latent vector for keys and values. And the dimension for the CKV is like DC, which is like much smaller than um, DH times NH, which is uh, the dimension for keys and values that you used to have in multi-head attention. And later on, like after this down projection, to get the keys and values, you can perform an up projection from your hidden from your latent compressed latent vector CKV. And this when you actually want to perform your attention, it's like the query metrics, like the query would be computed by WQ times HT. So uh, Q transpose K would mean like there would be a matrix multiplication between that WQ and WUK. So even this up projection can be merged into that WQ. So even that doesn't need to be computed. You can get away by only um, storing your like caching your CKV and without actually computing your keys and values, you can perform that attention. So that's like the high level idea of low rank compression. Even so, even if it is not needed, you can also like they also suggest that to reduce the activation memory during training, they perform a low rank compression even for the queries. So even for the queries, you can perform like a down projection of your hidden state to get a low rank um, compressed latent vector, which is like CQT. And then you can perform an up projection from that to get your queries. So this is like a high level idea, but as is, you cannot use it for multi-head attention because it's not directly compatible with rotary position embedding. Okay, so first let's see at a high level what is rotary position embeddings. The goal of position embeddings is to actually impart the position information, because if you look at the attention computation, it's like a dot product between your query and your keys, which are some representations of of the hidden states at different positions. So if there is no position information, there is no understanding for the model as to whether the tokens being attended to are in which order, how far are they apart, or like make some kind of use of that position information to to deduce various like the meaning of that token in context. Hence, embeddings are important. So the key idea between rotary position embeddings is to have like a version of position embeddings which is only dependent on the relative distance or relative positions between any tokens, and not the um, absolute positions of the token themselves. So here is like I'm like sharing the reformer paper where this was introduced, like a general form of the rotary position embeddings. So just like earlier, we saw that like to calculate your queries, we would uh, take a linear projection uh, of your hidden state using like a weight matrix. Here we also multiply instead of adding a position embedding, we actually multiply it with a rotation matrix, and we'll see how that is done. And the goal is to actually ensure that when we take this dot product between a hidden state at like a query from a hidden state at position m with a key from a hidden state at position n, it's just a function of the two hidden states, xm and xn, and some function of the relative distance between m and n, and not the absolute position themselves. So the way they implement it is to actually have this function as a weight matrix transformation followed by a rotation matrix. So this for this rotation matrix, what they do is divide your d-dimensional space into d by 2 subspaces. So like take pairs of dimensions like 1 and 2, 3 and 4, 5 and 6, and finally um, d minus 1 and d, and take this pair of dimensions and then rotate along this so this matrix would rotate along this two dimensions by m theta 1. So here m is the position of like this matrix is dependent on the position of the token. So this for the position 1, like for the dimension 1 and 2 rotated by m theta 1, for position 3 and 4 rotated by m theta 2, and finally for d minus 1 and d at dimensions rotate that subspace by m theta d by 2. So these theta are nothing but like the frequencies, or like they control the angular frequency by which these uh, angles are the frequency by which these rotations are happening, and they are of varying varying frequencies. So 10,000 to the power minus 2 times I minus 1 by d, where I belongs to from 1 to d by 2. And this rotation, like the interesting part about this rotation matrix is that you rotated like your queries by a rotation which is uh, like uh, a function of your m, and then you rotated your keys by by rotation matrix which is a function of the position n. And if you look at the at this q transpose k, and you replace this q's and k's by the functional representations in um, the like the rotary position embeddings for formulation, you would see like this transpose becomes XM transpose WQ um, transpose RD theta M transpose and RD theta N WK and XN. And if you combine the two matrices, um, it would become like a rotation matrix of theta of n minus m. So basically here the only position embedding position representations coming here are these, and this is just proportional to the difference in the two in the positions of the two tokens. Um, So that's like a general form of rotary position embeddings. You multiply it by a rotation matrix as well as a weight. So now if we wanted to directly use the rotary position embeddings, we cannot do so in this current formulation where we have compressed like your queries and keys and values into a lower dimension. Um, so the issue is that if you were to apply this position embeddings, you would have to do it at the keys. That is like after this a projection is uh, like a projection matrix is multiplied. Only after that you can apply this rotary position embeddings. But that would mean that you would have to calculate this WUK, and then you cannot cache just the compressed vectors, and you would have to like store the entire k. Um, so in a way, you cannot get the efficiency of low rank compression if you want to use it as is. So they have like a different strategy in this paper. So the solution that's proposed in the DeepSeek V2 paper is called like have is to have like a decoupled rotary position embedding. So not all the dimensions of your like queries are reserved for like have your position embeddings. So for example, let's look at the equations to understand like how it is implemented. So you decouple your query into two parts, like QC, which comes as an up from like the up projection of your like your latent query vectors, um, and then your QR, which consists of both the uh, tokens information as well as your rotation matrix. So basically, you compare like apply like rope over your compressed query to get like this QRT and you get it. You have like a separate query, certain dimensions for certain query reserved like with having this rotary position embeddings, and that makes your queue. For keys also it is something similar. Your ith like for your ith head and tth time, your keys also have like two parts, like the first part coming from your compressed keys, and then the second part is actually KRT, um, which again comes from applying rope to your hidden time step, but this one is shared among all heads. The rest of the attention computation is like similar to what you had before. So now instead of caching uh, in multi-head attention, you would have to cache all your keys and values. Right now, you would have to cache just let's see the DeepSeek V3 diagram. So here, like the dots represent the things to cache. So you can just get away by caching your CKVT, and can be like these can be calculated by using some intelligent matrix multiplication where the up projection matrices are merged um, with your keys and the value uh, transformation matrices. And the other part to cache that you would have to cache is your KR, um, which is basically coming from your um, hidden time step, and then like rotary positions being applied to it. So these can be cached and reused. These can be computed on the fly. And yeah, similarly, like because even it was not needed, but on the query side, you perform this latent down projection followed by up projection. It reduces your um, inference memory requirements or your activation memories. So the that's like the total calculations for multi-head latent attention. Like once you have these queries and keys, the final computation is again same as before. Um, the keys and queries are used for each of the heads are used to calculate the attention scores, and then you use this like use softmax to convert that scores into like like numbers between 0 and 1, and then you use that scores to uh, take a weighted mean of your values corresponding to that head, um, and that gives you the output for that head, and then the final output is just like a transformation of your outputs from each of the heads concatenated together. That summarizes the entire multi-head latent attention process. And the advantage is that during inference, all you need to cache is like the decoupled key, um, as well as your um, latent vectors, CKVT. All right. So let's come to the mixture of experts part of the model. So the DeepSeek MO is like a mixture of experts model, like a mixture of experts layer, and it kind of replaces the feed-forward networks that's part of the transformer architecture. So instead of like a feed-forward output, you have like a sum of outputs from various feed-forward networks, and these are called experts. And the basic idea is that instead of a token passing through all the feed-forward networks, you only route it through a subset of those, and you have like a gating mechanism that decides based on the token which expert to route to, and this feed for every each of this different feed forward network is called as an expert. For DeepSeek MOE, as compared to other architectures like G Shard, you have more number of experts, like more number of finer grained experts, like experts with lower um, dimensionality, but a higher number of such experts. And some of them are called shared experts. So shared experts are ones which are like to which the tokens are always routed, and then the other ones are called like the routed experts. So among these routed experts, only a subset of them, namely uh, K of those experts are activated for every token. So let's look at the actual equations of this DeepSeek MOE in DeepSeek V3. So the output at any time step t from this DeepSeek MOE layer is like the UT, which is like the input to this layer, and then it is followed by some from various experts. So among the shared experts, they are always activated. So like output from the FFNs of each of these shared experts. NS refers to the number of shared experts, and this is followed by like gate gated outputs from the routed experts. So these gates decide which of these routed experts are active, and these are like sparsely activated, which means that only k among these uh, fine-grained routed experts are active for any token. So for any token, basically a dot product with of that like to find out whether uh, a a token needs to be routed to an expert. You find like the dot product of that um, token's representation with that of an centroid vector of that expert. And this is again, I think this is a learned latent vector. Learned vector, and the dot product is gives you like a score or an affinity score of that token uh, to that routed expert. Um, so this is called the token to expert affinity. When you compute this dot product, you get like a uh, token to expert affinity, and a sigmoid is applied to squash this value between 0 and 1. This is then normalized. Okay, I think before normalization, yeah, I think this is used to calculate the affinity scores. So based on the affinity scores, if like the uh, instead of a token being routed to all feed forward networks with those affinity scores as weights or of those gates, actually there's a sparsification that happens. That is, this SIT is transformed to zero if those if it does not belong to the top k, and otherwise it remains SID. So like the scores or like the affinity scores for the top k experts for the token are preserved, and the rest are set to zero. And here top k is like kr, where kr like kr number of experts are activated. And post that there is another normalization step that happens, so that I think all of these scores add up to 1. So this is how the gate scores are calculated, and then your final hidden state is just like a gated sum of these output from these feed forward networks, and these gates are calculated in this way. So this ensures that only kr number of routed experts are activated, and then all the ns number of shared experts are activated for every token. Okay, so we have seen how for every token it is routed to only a subset of all the experts. So if you do not have like a load balancing strategy, it can lead to routing collapse. That is, if some if some experts were selected initially, all the tokens would may learn to rely on only those experts, and over time there would be like a routing collapse. That is, those experts would always be overloaded and the others be underloaded. So you need some load balancing strategy to ensure that all these experts are utilized, and as well as uh, all the tokens do not get passed on to like only small number of uh, experts all the time. So conventional solutions usually rely on some auxiliary losses, which kind of punish if some experts are overloaded. But like in the past, they have done this analysis which shows that these losses, since you train the model through a sum of losses. These losses may impair your model performance. So in DeepSeek V3, they came up with an load-free, like a auxiliary loss-free load balancing strategy. So a strategy to balance various experts without using any loss. So the way they actually implement it is using a bias term. So as we see here, these gates were computed from these sigmoid scores, and in such a way that apart from the top k, the rest score like affinity scores are set to 0. So in this load balancing strategy, they add like another term to their affinity scores called the bias, and this bias is like they have like a separate parameter for every expert, and the bias is such it is used to just determine like the top k. Um, so if expert is underloaded, you would want that bias to be slightly high so that it is preferred. And if a expert is overloaded, you want this bias to be slightly low so that it's not it's lesser preferred relatively. So basically, in training, the uh, expert load is monitored on the whole batch, and at the end of each step, that bias is decreased or increased by a factor of by a term gamma, based on like whether it's overloaded or underloaded. So this gamma is like a hyperparameter and it's called the biased update speed, and thus using just this bias, it is able to handle the um, kind of dynamically handle this routing without using like a explicit loss to or an explicit auxiliary loss to ensure that the load among all the experts is managed. So this is different from what was present in the DeepSeek V2 paper. So in DeepSeek V2, you had like a similar architecture, although there was no normalization uh, at the end of this GIT, and also this SIT was a softmax here. So that's like a minor difference. And the other one being the auxiliary loss for load balancing. So you had like a loss which would kind of be uh, low only if the load among all experts is well balanced. If you look at look at all the tokens across all the batch examples. So that's a comparison of the expert level balance loss in DeepSeek V2, which they found that it sometimes impairs the model performance by interfering by its gradients interfering with that um, of the uh, learning the actual supervised learning loss. So although they use a load balancing strategy which is loss free for balancing across all the tokens across batches, within a sequence they have like a sequence wise auxiliary loss, and the goal of this loss is to have like a encourage that the expert load on each sequence is balanced. To do that, the loss is like a sum of losses, like a sum of some terms for each of the experts. Here, I is like the index of summation for all the experts from 1 to nr, which is all the routed experts. So it consists of two terms like fi and pi. So Fi is nothing but like the number of tokens where that expert was selected for routing, multiplied by a scaling factor. And for PI, like first you for every expert and a time step, like time step t, you find like what's the affinity to that uh, expert normalized by the affinity scores to all the experts. That gives you like a normalized score. And then for an expert, the value pi is just the average of such normalized score across all time steps. So it basically gives you like across time steps what's the average normalized affinity score for that expert. And since you want this uh, s- like uh, like all the across tokens, you want this scores to be distributed, like you want these scores to be distributed across various experts, and only then would the total loss be low. So that's the um, strategy, or like the loss function, to ensure that the load across like within a sequence is also kind of uh, balanced across all the experts. So along just like DeepSeek V2, in even in DeepSeek V3, you have like a restricted routing mechanism across nodes. So each token is only sent to at most m nodes. And how do you select these m nodes where you want to send these tokens to? So basically, you like the experts. Each node gets like, so if you look, um, there are like kr number of uh, experts that can be active, and if there are um, uh, m nodes, at most like m nodes, so each of those nodes would get kr by m number of experts on average that would be active. So this is the value. These are the number of uh, experts that get to vote, like which node to select. So the affinity scores from experts from KR by M top experts on each node are used to vote for nodes, and only M at most M nodes are selected to send each token to. And under this constraint, they are able to show that the training framework can achieve like full computation communication overlap. As compared to DeepSeek V2, in DeepSeek V3, there's no token dropping. They see that they have like an effective load balancing strategy, and hence they don't have to employ like a token dropping mechanism. Let's see in DeepSeek V2, what was the token dropping strategy. So basically, you would have they followed an idea which was present in the scaling vision with sparse MOE paper. They would be inspired by that. They would drop tokens with the lowest affinity scores on each device until reaching a computational budget. So uh, each kind of uh, each expert would have a budget and of the number of tokens that it can handle, and then there would be a way to sort tokens by importance, and tokens each token would get to choose, like once sorted, would get to choose its top k uh, top K experts, and they would get dropped if none of them were available. So in addition, they would ensure like the approximately 10% of the training sequences, like tokens belonging to approximately 10% of the training sequences are never dropped. However, this token dropping strategy was not needed in DeepSeek V3. So the final part of the architecture that we'll discuss today is the multi-token prediction part. So they investigate a multi-token prediction objective for DeepSeek V3, and the main goal is to improve the training performance, or like the training data efficiency. So usually, like in past, other papers have explored predicting like D additional tokens using individual uh, independent output heads. However, in this case, they sequentially predict tokens one at a time sequentially, um, up to like a depth of k. For DeepSeek V3, this k is equal to 2. That is, for a given time step, they try to predict the next token and the next after that and the next after that. So the details of the multi-token prediction are there in the following section, but let's look at the image first. So first of all, like if you look at this architecture, say at um, for first time step, you're trying to predict the second token. For second time step, you're trying to predict the third token, and so on and so forth. So this is your usual next token prediction module. So for the multi-token prediction part, there's another component, which here also at time step at this position, tried here it tried to predict like the third token, but it will also try to predict the fourth token using what it has predicted up till here. So just to actually look at the architecture, at the first MTP module, it will try to predict token t plus 1 um, at ith time step. In the like main model, it's trying to predict like the I plus 1th token, and at the kth MTP module, it will try to predict t of I plus 1 plus kth token. And how the architecture looks is that you have shared embedding layers. Here is your out like the L layers of your transformers, followed by an output head. These output head uh, convert your last layers output into logits for your cross entropy loss. Um, this output here, before the output head, is passed to your next MTP module. Um, and then uh, the input tokens are shifted to the right by one, and those are passed to the embedding layer. They are concatenated like after RMS norm, and then and after concatenation, if you look at here, in a way, the last layer here, uh, before the final output head, somehow contain like information about the next token. So when we are performing this concatenation, in a way, it's all these tokens after the last layer already aligned to the next tokens, so they are in somewhat a similar space. But then there is a linear projection layer, which transforms it from um, 2 times d dimension to d dimension, and then kind of these two representations are combined. I'm assuming that here also we are doing teacher forcing. That is, you exactly, since this is training, you exactly know which tokens would be there. So you actually use them instead of looking at what is being predicted at the output head. Uh, so once you get the output from these transformer layers, merge it with the embeddings of the like times input tokens shifted by one, merge them up, move them through a transformer block, and have then an output head, which is again shared, which is they're shared in parameters, to then get, which then gives you like a logit for the time step t plus 1. And then the next module would we have like a very similar architecture, and it would try to predict like the next token. So this is like the multi-token prediction architecture at a high level. So the as I said, like first it uses like d sequential modules to predict d additional tokens, and the kth module consists of a shared embedding layer. These embedding layers are shared. Similarly, the output heads are shared um, between the different modules. So there is this output head, a transformer block, and a projection matrix. For the ith token at the kth prediction depth, we must combine the representation of the ith token at the k minus 1 at depth and the embedding of the I plus kth token embedding. So if you look at this particular module, for this kth module, the representations for the ith token are combined from the k minus 1th um, modules output, as well as I plus kth token embedding, which is coming from here, and both of them are are then concatenated after like an RMS norm followed by a linear projection, so that like after the concatenation they are back to the same number of dimensions. So first they are we perform you perform RMS norm, then you concatenate, and then perform a projection back to d dimensions, as mk is d cross 2d. So from you both had like d dimensions, concatenated became 2d. After this mk times uh, this representation, it again becomes like d dimensional. So now you get the representation for the kth module and for the ith token. This is then passed through like a transformer block to produce the output representation. And finally, you apply like a same shared output head to try to predict the I plus k plus 1th token. Again, after the output head, you need to apply like softmax, and that gives you like a prediction probabilities for the kth additional token, that is I plus k plus 1th token. And the cross entropy loss gives you like the loss for the kth multi-token prediction module. So these multi-token prediction modules, those losses are called like LKMTP, and then it's like the standard cross entropy loss. But if you look at its contribution to the final loss, the losses for all the kth modules, all the k module, all the I think d modules are then summed up, and then like averaged, actually not summed up, they are averaged and then multiplied by a factor of lambda, which kind of is a weighting factor, and you can tune it to see how much of relative importance you would want to give MTP losses as compared to the standard training losses. So at the time of inference, it can be discussed. So I guess their strategy was mainly to improve the performance of the main model. And so it can be these additional modules can be discarded. However, if you want to use speculative decoding, these additional predictions can be used for speeding up the generation, like improving the generation latency, or speeding up the decoding process. So that was a overview through the entire architecture of the um, DeepSeek model, DeepSeek V3 model. If we go back to the diagram, uh, basically you had like two major components, which is like the attention and the feed-forward network within a transformer block, which are modified. Like the attention is modified to multi-head latent attention, and the main goal was to use these compressed latent representations to reduce the KV cache and have some technique to actually make it compatible with rotary position embeddings, while being memory efficient. The second solution was modification to the feed forward network, where instead you have like a sparse DeepSeek mixture of experts model consisting of like some shared experts and some routed experts, using a gating mechanism. Only a subset of these routed experts are finally used, and the final feed forward output is a sum of the outputs from each of these individual experts. And you have some losses, not just for like one of the losses that you have to train these models are the cross entropy loss. Then apart from that, you also have losses to ensure that there is balancing, load balancing within a sequence inside these mixture of expert model. And the additional loss comes from the multi-token prediction part, where instead of trying to just predict the next token, you also try to predict the uh, next 1 plus d tokens as well, using a sequential MTP module. So that's like the overall DeepSeek V3 architecture. In further videos in this series, we'll go through the other components of the paper. Thanks for watching, and thanks for joining the for watching this video. Um, Please do like and subscribe. There may be errors within this video as I am making it just to learn it on the side myself. So happy to take any questions uh, and try to clarify any errors in the making. Thanks for joining.